says rec, REC. Good? All good. All right. So, this coming back to this point of symmetry. The first thing when you see these problems, the electric field problems, when you have a set of charges, the first thing you should look at is you should see if there is any symmetry that you can see it in here. Now, let me ask you the question. Do you see any symmetry here?
Yes. Yes.
What is the symmetry you see? That's it. That means what? That means if I look at the electric field due to, for example, due to charge 1. Remember how we get the electric field? The electric field, it should be along the line connecting these two, right? Yeah. Let me call this E1, electric field due to charge 1. Now, this guy will have two components, right? Yeah. It will have an X component, E1X, and E1Y. Okay? Right? Okay? That's good. How about this guy here? If I calculate the electric field with this one, remember why is the direction this way? Because I place a positive charge here. Positive and positive will repel. Okay, so that's why the direction, if somebody is wondering why is the direction of the electric field is this way, because positive and positive will be. Similarly, if I calculate the electric field due to charge Q3, then I'm going to get something like this. Right? And then I'm going to get E3X and E3Y. What do you see immediately? Symmetry. What's the symmetry you already see here? The components, the Y components of the electric field due to charge 1 and due to charge 3, what are they going to do? Cancel. Okay? So that saves you a lot of time. So all you have to do in, let's say, in an exam situation or in a quiz situation, you say E1Y is equal to E2Y. Therefore, in this case, the sum of the forces along Y is equal to 0. Okay? That's symmetry. Now, then, for me, all I have to do is for these two charges, the only thing I have to calculate is the X component of these of the electric field, and in fact, I have to calculate it only once and multiply it by 2. That's another effect. That's another symmetry effect. Okay? And how about this guy here? All I have to do is just calculate the electric field at this point due to this charge, and I'm happy. All right? And so what we have to do, let's do E1 X, which is equal to E3X is equal to what? E1X is equal to E3X. Is equal to what? Is equal to 1 over 4 pi epsilon, which is K, right? Multiplied by the charge. Remember, he told me these charges are the same. By the way, if these charges are not the same, there is no symmetry. Right? Yeah. So you should write that down. The only reason we're saying this is because the magnitude of the charges is the same. Yes?
E1Y is equal to
E3. E3, sorry. Thank you very much. I said E3 and I wrote E2. Okay? Yeah?
If they're not equal, that means that E3Y and E1Y will cancel out?
Yeah, that's what I said. That's what.
If they're not equal.
If they're not equal, they're not going to cancel. No? No, they will not. If the charge and the magnitude of the charge are not equal, then they will not cancel out. Somebody had a question earlier there.
Me? No,
yeah.
I told you about it.
Oh, okay. Thank you very much. Yeah. All right. So, and this would be equal to what? Q. Remember, the charge is Q. So it's Q3, Q1 is the same thing. All of them are Q. And what is the distance here between this and this? Remember, this is D and this is X. Square root D squared plus X squared. Remember, I'm going to square it. So it's equal to X squared plus D squared. Okay, square root and you square root goes. Alright? So, and the direction, I need to know the direction. What's the direction E3 is equal to? Cosine this angle, right? And this angle is the same as this angle. These two angles are the same. Because I still have, because it's EX, I have to multiply it by cosine theta. And that's my theta. It happens to be it's the same as this. If I take the cosine of this angle, it's X over the hypotenuse. Okay? المجاور over الوتر. So this will be cosine theta. It will be written 1 over 4 pi epsilon Q X squared plus D squared, and then multiplied by X That's my adjacent over the hypotenuse, which is the square root of x squared plus d squared. Okay? And that is equal to, of course, if I do just simplify things, 1 over 4 pi epsilon, and then q x divided by x squared plus d squared to the power of 3/2. 1 plus a half plus 1 is 3/2. Okay? So I get the x component. If I want to find the sum of the forces along x, the sum of electric field along x, that is going to be twice this, because I have two components of this, right? This component is equal to this component, so twice of this, and that will be 2 times 1 over 4 pi epsilon, and then q x divided by this to the power of 3/2. Okay, that's why Ex due to what? Due to charge 1 and charge 3. How about the electric field due to charge 2? That's easy, right? What's the electric field due to charge 3? E2, let's call it E2. It's equal to 1 over 4 pi epsilon, and then you multiply Q, which remember this is Q. Q1 is equal to Q2 is equal to Q3, divided by the distance, in this case is equal to x squared. And by the way, this is I hat, so it's along x only. Okay? So if I want to find the net electrostatic force, what do I have to do if I want to find the net electrostatic force? Okay. Yeah, we add all three of them. So the net electrostatic force, E net, will be equal to this guy, 2 multiplied by 1 over 4 pi epsilon, and then I have Q x divided by the x squared plus d squared to the power of 3/2, and then plus that one over there, which is 1 over 4 pi epsilon, and then q over x squared. All of this along the I hat. All of this is along the I hat, which means it's this direction. The electric field is this direction. That's my net electric field, E net. Okay? The details, by the way, the details of the solution is written, or at least it's in the next slide. All right? So is it understood how we do the things? How we calculate the net electrostatic field due to several charges, 1, 2, 3. And we have to do them individually first. Right? We first calculate the electric field due to charge 1, the electric field due to charge 2, the electric field due to charge 3, and then I sum them up as vectors. Okay? And of course, in this case, it's along x, along the x hat, or the positive x. Why? Because we use something called symmetry, and we know that electric fields are highly symmetric provided the right conditions.
It's E2 or EX?
This is E2. E due to charge 2.
Where's the EX?
Because there is only one component.
Just in the X?
Yeah, there is only one component. That's a good question here. See, you said, where is EY? Well, there is only one component. In the case of positive charge here, it will be only EX, which is along the positive X component. Yes?
Question. About the 1 over 4 pi epsilon is equal to 9 times...
Yeah, that's key. 9 times 10 to the power of 9. Yeah, we can definitely. Because the second part of the question, okay, let me just, now because as I said, the solution is here. So again, it's exactly what we did. E net is equal to 0 along the y hat because of symmetry. And then E net along x, we have to E1x, E2x plus E3x, which is 2 E1x, they are equal. And then the total is this, right? Which is exactly what we found there. This is E2x, right? And then when you add everything, that's what we get here. Okay, you have the cosine, this is E3x, the cosine, and all of this business that we've done. So I think there is more detail. The answer is here. Okay, E2x, E1x, and then you just add, this is if x is equal to 3 and d is equal to 4. So he gave you the second part. Calculate this when x is equal to 3 meters and d is equal to 4 meters. So all you have to do is just plug these in. And Q, he said it's equal to 6 microcoulombs. Q is equal to 6 microcoulombs. So you plug that in, and that's the answer that you get when you add everything up. That's the magnitude. And of course, the direction is along the positive item. Any questions on how to calculate the electric field? Okay. Now let me just ask you a question. Now I know what the electric field here at this point is equal to something like 15 kilonewtons. So the electric field at point P calculated to be something like 13 kilonewtons per coulomb. Okay, so kilonewtons per coulomb. That's what we found here, right? The kilo 1,000, right?
Yeah.
Okay, everybody knows that. Now, what if I ask you to calculate the force of a charge? Let's say I bring a charge. I'm going to call it 3 microcoulombs or whatever it's equal to. And I say, if I place that charge at point P, what is the force on that charge?
We multiply it by D
F
is equal to
is equal to U multiplied by E. That's it. So the force experienced by any charge I put at point P, all I have to do is just multiply that charge, which is now, let's call it Q4. Okay. Q4 multiplied by the net electrostatic field. That's it. Okay? So that's a point that you should keep in mind. Any questions? Okay, let's keep on trucking now. I've added.
What's the difference between E and F and F? The whole force is there.
Yeah. E.
Why is that?
Wait. The difference between E and F? What's the difference between E and F? E is the electric field, and F is the electrostatic force. Okay? Remember how we define the electric field. The electric field is equal to F divided by, or the force per unit coulomb. So the force felt by each coulomb, that's called the electric field. Okay? So the electric field is a little bit different than the force, the net electrostatic force. Okay? Alright, so one thing that I added this year is, I don't know if you're familiar with it or not, but there are the big universities like Yale, MIT, Stanford, Colorado, big universities now, they're having their courses, all the material, PDF files, notes, PowerPoints, exams, everything online. Okay. The one that I often consult is the MIT open course files. And I gave you the link here, so if you guys, I'll post this today, this is updated. So, and one of the things that the advantage that I'd like you to sort of get out of this is you say, okay, I am taking the same material as those students in MIT taken, which is something for you to say, I'm just like everybody else, there's no. And I've taken 3 of their questions, examples in the, actually it's not examples, it's problems in the notes, and if you click here, you get the complete notes. And I would like you to try these. I will solve them. I don't think they have the solution there, but I'd like everybody to try solve these questions. The first question is simply asking you to find calculate the net electrostatic force on charge 9, charge 3, so minus 6. And the second one, he wants you to calculate the electric field at this point, which is located between or somewhere within 3 charges, which we have magnitudes, specified magnitudes there. The third question, he gave you 4 charges, and he wants you first to find the electric field on charge Q, on this charge, the net electrostatic field on this charge, magnitude and direction. And the second one, he wants you to find the net electrostatic force on that. If you do these 3 examples, you're in business. That means everything we've done so far, you understand it, and things are going very well in terms of understanding it. So again, I will consult these, and maybe I will bring some from the University of Colorado one time, and another time from Stanford and so forth. Okay, just to get you the the confidence that you can at the international level, inshallah.
Are
Okay?
the
Yeah,
answers-
question?
Are the answers given?
I did not check, but if they're not, I'll give you the answer. Okay, but I'd like you to attempt first. Attempt these first. So these are updates. I'll post the updated version later today, inshallah. Okay. The second thing, or the next thing that I wanted to discuss today, which I mentioned at the very beginning of the lecture, is the concept of uniform electrostatic field and the motion of particles inside or within this uniform electrostatic field. Let me just remind you of what we want to do. Now, when you took kinematics in first year on physics 1, when you took kinematics and you had these 3 or 4 equations, the first one was V2 is equal to V1 plus AT. Second one was, I'm just going to write them in one dimension. Delta X is equal to V0T plus a half AT squared. And the last one, yeah, is equal to V plus 2A axis. Okay. What's so special about these three? There's the average one. The first one was the average velocity. I did not write it. I usually just these are the important ones for us. What is so special about these equations? Did you guys call it constant acceleration at that time?
Uniform.
Uniform. Okay. I will accept constant if you're happy, if you know the meaning. So, but the magic word is that these kinematics equations, what they have in common is they all have what's so-called uniform acceleration. What is meant by uniform acceleration?
It means that uniform does not change acceleration.
If I say I have a car that is moving with a uniform acceleration of 1 meter per second square, what does that mean? That means every second the velocity is increasing by 1 meter per second. Okay. Meaning, if you do not like this or this is too long, the velocity is continuously changing.
At the same rate.
At the same rate. Thank you very much. Okay. So, but the acceleration means that there is continuously the velocity is continuously changing. Now, later after you finish this, then you came to Newton's second law. And then you had something like this. The sum of the forces is equal to MA. Right? And you said this is uniform if the constant. Okay? If the force is constant, then the acceleration is uniform. If you vary the force, then you have to, I'm sure I don't know if you got into that or not, but variable forces will give you something different. Okay? So, and if we go back a little bit, and then you see the reason we had constant force is because we're walking somewhere near the surface of the Earth where the gravitational field is uniform. If you're close to the surface of the Earth, the gravitational field, the pull, the attraction is very uniform. Okay. We wanted to do the same thing. We wanted to establish something where we have the electrostatic field is uniform. And the way we're going to represent the uniformity of the electrostatic field is by parallel lines, parallel electric field lines. So if I have a charge here, positive, right? Positive. And then I place, for example, if I wanted to calculate the electric field, then this charge is continuously, periodically repeated, so it's uniformly distributed. And then if I calculate the electric field at any point, then the electric field here, if I take a positive charge, then it's pointing down. If I take that positive charge here, it's pointing down. It's pointing down, so I can say E is uniform. E is uniform. Okay? So the electrostatic field, I will tell you in a few minutes, maybe towards the end of the class or next class, that how can we generate a uniform electric field. But just for now, an electric field or a uniform electric field is depicted by parallel field lines that they are separated by the same distance. Okay, and later on will become clear why this is. But for now, all we want to know, or all we want to make sure that, all we want to make sure we understand is that we want to produce or to deal with something called uniform electric field. Okay, so it's equal wherever I am, I feel the same magnitude. Wherever I am, it's the same electric field, uniform. Okay. Now, if I have a uniform electric field, I'm coming back to your question. Just give me 1 second. If I have a uniform electric field, what does that mean? That means if I place a charge here, let's start with positive charge for simplicity. If I place a charge, then F is equal to QE. That means what? If this is uniform, remember Q is a scalar quantity that even though it has a negative and positive sign, it's still a scalar quantity. Okay? So if this is Q, is some number, a multiplication, and I multiply it by some vector, then I'm not going to, the only thing that it's the magnitude will be the same. The direction may vary, but the magnitude will be the same. So what does that mean? That means I will end up with a constant force. If I have a constant force, then what do I get? Uniform acceleration. Uniform A. And if I have a uniform acceleration here, when this particle is released or kicked or whatever, then it's going to move under uniform acceleration. And this way I can apply to describe its motion, because remember the concept of uniform electrostatic field and the motion of a charge inside this field. It's just like we wanted to describe the following. We wanted to describe this to the Earth, and we wanted to describe the motion near the Earth, where the gravitational field is considered to be constant. Same thing here. We wanted to describe the motion of the charge in a uniform electric field. So as soon as I know what the electric field looks like, then I can calculate the force, and after that I can calculate the acceleration, and from there I can apply my kinematics equation. Okay? Let me answer a couple of questions people have. Yeah, what's your question?
In the parallel lines, A is always uniform?
Yeah, if the electric field lines, let's do it the other way. If the electric field lines are parallel, then the electric field is considered to be uniform. Okay, that's an indication that the electric field is uniform. In fact, when we talk about flux, when we talk about calculating the electric field and so forth, we'll come back to this again and see exactly why. Now, I promised to show you how we calculate the electric field, or how do we do this. We do it using something called the parallel, does anybody know? Yeah, parallel plate capacitor. We're going to come back to this in much more detail when we talk about the electrostatic energy, because the capacitor is used to store electrostatic energy. So we'll come back to this again. What is the parallel plate capacitor? The parallel plate capacitor is simply a line of two charges. One of them is positive and one of them is negative. They have exactly the same magnitude, except one of them is positive and one of them is negative. What is the consequence of, what is the result of this? Or what's the significance of this? That, remember what the electric field lines look like. The electric field lines, they originate from a positive charge and they terminate at a negative charge. That means what? That means my electric field will be originating here and terminating here. Okay? So that I have a uniform electric field inside and electric field equal to 0 outside. Okay? So the electric field inside the parallel plate capacitor, En, is uniform. Uniform, in fact, is equal to Q over epsilon. And I'll tell you why is it equal to Q over epsilon. Okay? So right now, just believe me, the magnitude of the electric field inside the parallel plate capacitor is equal to Q over epsilon. Okay? And QA over epsilon. Anyway, I'll come back to this. Q over epsilon. That is epsilon A. Epsilon A?
Yes.
Yeah, Q over epsilon A. Sorry, I forgot that. If we take sigma, then it's sigma over epsilon, and I'll tell you what sigma is. So I just get confused with the other two. Okay. All right, so the electric field inside is uniform and its magnitude is equal to Q over epsilon A. Right. Once, see guys, all you need to know is the charge, because this is, remember, the charge has the same magnitude but opposite direction. If you know what the charge is, and I'll give you what the charge is, and if you know what the, remember that's parallel plate, parallel plate. If you know the area of the plate, and the plate can be rectangular, okay, which area will be this time is that, or it can be circular, disk, in the form of a disk, which is equal to pi r squared. Or it can be a square where it's L square or H square or A square. But this is the area of the plate, and that's the charge on the parallel plate, and epsilon is the epsilon naught that we're used to, which is the permittivity of free space. Okay? So the idea here is that, let me actually use this diagram that I had to illustrate this further. So the idea is that if I have a parallel plate capacitor like this, right? A parallel plate capacitor like this, then the electrostatic field inside in the region between the plates is uniform. If the electrostatic field in the region between the plates is uniform, that means the force is constant. And if the force is constant, the acceleration is uniform. If the acceleration is uniform, then use kinetics to describe the motion of the charge inside the electrostatic field. Okay? Let me write them here because we're going to do an example. Okay, so first E is equal to, we just saw it's equal to Q over epsilon A, which is uniform inside. Remember, this is for a parallel plate capacitor. Parallel plate capacitor. Why do we use the parallel plate capacitor? Because it provides us with a uniform electrostatic field. Okay, that's a special case. And from here, I can get for a charge Q. For Q, I have F is equal to QE. Right? And then F is equal to MA. And this F, if you want to replace it by QE, is equal to MA. Don't forget all the vector signs. Okay? And once I find the acceleration, then I can go back and describe the motion of the particle using my kinematics equation contribution. Okay? The only thing that I thought somebody would ask me is that, wait, this guy has two signs, positive and negative. It can be positive, it can be negative. What's the effect of a negative sign? If the charge is negative, what's going to happen? What's the opposite direction? Let's go back to our parallel plate capacitor. Okay, so I have a parallel plate capacitor. I'm going to use the same thing. Positive, okay, negative charges, and then I have the electric field uniform. Okay, so my electric field is uniform. Right? And instead of placing a positive charge, charge, I'm going to place a negative charge.
So
it will go, put it in a different way. It will move
to the plus.
opposite to the field. Okay? So you should write that down in your own words. A positive charge will move along the direction of the electric field lines. Okay? And a negative charge will move opposite to the direction of the electric field lines, or the field in this case. Okay? Yeah?
In an electric circuit, it's negative, right?
Say again?
In an electric circuit, the charge is negative?
Don't worry about that. You know, in an electric circuit, the charge is moving. We're talking about static. All of this is electrostatic. Okay, so an electric circuit will be later on. Okay? So is everybody happy? Because this it always gives students, sometimes they don't pick it up. If you have a negative charge, all it's going to do is going to go opposite to the direction of the field. Right? In fact, later on we'll explain it in terms of potential energy. We know that objects like to move from high potential to low potential. Once we talk about electrostatic potential energy, we'll come back to this again and discuss it in terms of potential. Okay? All right. So I think it's time for us to do an example, just to see how we're going to do that. By the way, before we do the example, do you guys remember the difference between when you drop or release a mass, or when you kick or eject a mass?
Yes.
What's the difference?
The velocity initial.
Nothing. No acceleration. No acceleration.
Initial.
If I drop a mass or release a mass, the initial velocity is zero. If I kick or eject a mass, the initial velocity is not equal to zero. Okay. So in the parallel plate capacitor, if I release a mass, okay, where will it go? What's its path?
Down.
Okay,
Along
you should have said, guys, now you should have said, well, it depends on its sign of the charge. Right?
Yeah.
All right, you guys did not say that. Okay. So now let me just say, because this is important. So suppose that I have my positive charge here, or positive plate, I should say, right? And my negative plate here. And then I release a positive charge here. What is it going to do?
Along the positive.
It will go straight down. Okay? If I release it, it will go straight down. Okay, what if I come here and I have an electron? Okay, an electron will go where? Up or down? Up, because it's negative and the field is down, right? What if I come an electron here, E, and I kick it with some initial velocity, Vx is equal to something. So I kick it horizontal, just like when you kick a ball. What is it going to do? It will go? What is this motion called? You guys thought you're not going to see physics 1 again? Well, it's after you. Physics 1 is always after you. Okay? So this, if you kick it here, then it will do this. It's projectile motion. Okay? And then we have to go to use our projectile motion equations to describe this. By the way, there is always, no exception, a question about this. And maybe the first quiz, the first exam, is the motion, what I wrote there, motion of a charge inside a uniform electrostatic field. If you want to really understand it, just think it's exactly, no, I shouldn't say exactly, it's analogous to what you had in physics 1. It's analogous. In physics 1, you assume that the gravitational field is constant near the surface of the Earth, and then your acceleration is constant, uniform, and then you apply the kinematics equation. It's the same thing. Your electrostatic field, instead of the gravitational field, is constant. That gives you a constant force, and from there you get uniform acceleration. You can apply the same thing. Okay, yeah, question?
Sir, when we're giving an initial velocity, is it only horizontal?
Well, you can't give it anywhere. I'm just giving you the example. Yeah, you can give it anywhere you want. You can kick it this way if you want. Right. But I'm just giving you the example to indicate, just to make sure that you guys remember the. And remember, in gravitation, the parabola is always like this. Right? Here it's not restricted. You can make it go up, you can make it go down, you can make it go. Anyway, it depends on how you set the electric field. It depends on the electric field. Right? So let's take. So this is the parallel plate capacitor, and this is simply an explanation of how we see zero outside field and zero outside field and uniform field inside. Now, just quickly, because I'm coming back, I will come back to this very in more detail. The electric field, if you have a positive charge here, the positive test charge here, positive, negative, it will give you electric field this way. Positive and positive will give you electric field. If these guys are very close to each other so that the distance is irrelevant, what is going to happen here? The net electrostatic is equal to 0. Similarly here. But if you're inside and you put your positive charge here, so E positive will be this way, positive and positive will repel. And positive and negative will attract. So both of these vectors are this way. When you add them up, you get the uniform electric field. So just write it down. The electric field inside the parallel plate capacitor is constant and non-zero, and the electrostatic field outside the parallel plate capacitor is always 0. Can somebody repeat this? Okay.
The electric field inside the
Parallel plate capacitor?
yeah will be constant. Why not 0? And outside would be 0.
Excellent. Okay, make sure you say it's uniform or constant.
Uniform,
Okay? Now, I'm making this infinite for a purpose, where again, you should come back to it. Because you have to be away from the edges. If you're close to the edge, then you're going to have something like this. It's called the edge effects. But for now, we're just talking about somewhere in between. Okay, did you guys all get this statement here? You did it? Okay. The electrostatic field, guys, if you missed the statement, the electrostatic field inside the parallel plate capacitor is uniform, okay, and outside the parallel plate capacitor is 0. Okay. Now, by the way, this has a statement, guys. This statement has a huge implications when it comes to applications. Just so that you pick it up very quickly. Now, what happens to a charge if I put it here? If I put a charge right here, what's going to happen to it? Nothing. It will feel nothing, right? If I put a charge here, absolutely nothing. It's just like nothing exists. But if I put it inside, it's going to move. And that's the power of the application of the parallel plate capacitor. It's a very, very important device in electronics, in electrical engineering, like physics, and everything. It's very, very important. It has a unique characteristic where the electrostatic field outside is equal to 0, and the electrostatic field inside is uniform, and it's equal to some constant value, which is Q divided by epsilon. All right? Okay. So that's just an explanation of what I said, and this is a summary of all the things I mentioned about the parallel plate capacitor. Yes?
Doctor, you said...
Guys, I want to hear the question.
The rule here, it's Q divided by absolute in A. Is the area going to be always rectangle? Like this?
It will see it. It could be a circle, a disc, it could be a rectangle. We'll see. They will tell you. Okay, so the area, the plate, the only condition is that they are parallel. That's the only condition. But they could be circular, they could be rectangular, they could be square, they could be anything. Okay? Any shape, I should say, any two-dimensional shape. Yeah.
The electrical field that we're going to stay on here,
Uniform.
uniform?
Yeah. Inside between the plates here, it's always uniform.
We'll stay on uniform?
Yeah. Uniform, and we know its direction. Okay? The direction of the electric field, because this is often a question. The direction of the electric field inside the parallel plate capacitor is always from to negative. Okay, you have a question?
Electrical field inside is always uniform, right?
Yeah.
So acceleration is always uniform.
Yeah, that's the idea. That's the whole purpose of this. Okay? Okay, this is the edge effect that I told you. Okay, if you're close to the edges, the field is not uniform. And that's why we say ignore the edges and we're somewhere here, where we guarantee the electrostatic field is uniform. Okay? As I said, I mean, let's look at this example here. Very quickly. Guys, please. Okay, we have a parallel plate capacitor that consists of two circular, somebody was asking about the dimensions. They'll tell you, a circular order. So in this case, the circular electrodes, each one of them has a radius of r equal to 0.1 meter, separated by a gap that is equal to 1 millimeter, with opposite charges of magnitude equal to 20 nanocoulombs. What is the electric field between the plates? Quickly. What's the electric field between the plates?
It's equal to Q over
The electric field between the plates is equal to Q, which is 20 nanocoulombs. 20 times 10
minus 9.
Okay, and epsilon, we should know.
Yeah, 8.85.
Yeah, somebody knows it. 8.8 times 10 minus 12, right?
Yes.
Okay, and then the area. What's the area? R squared. What's R? 0.1. Square. It's in meters. 10 centimeters. Okay? Is this the radius? Oh, it's the radius. Yeah, it's the radius. I told you that. Yeah. If it is the diameter, then you have to divide it by 2. Okay, so that's your radius. That's very easy. What is the direction? What's the direction of this mechanism? Suppose that I have the plates here. This is positive, and this is negative, and these are my circular plates. What will the direction of the electric field be? Yeah. Whenever you draw your electric field, make sure they are equally separated, parallel, to indicate that it's uniform. Okay? All right. So that's the question. What's the electric field? That's fine. Okay, there you have the solution here. All right. We talked about the motion, the difference between a negative charge and a positive charge. If it is a positive charge, then the force is along the electric field line. If it is a negative charge, then the force is opposite to that. Okay, so if it is to move, it's going to move in the opposite direction. And F is equal to QE, and A, the acceleration, is equal to F over that, over M, and it's Q over M multiplied by E. Okay? If E is uniform, then A is equal to also Q divided by QE divided by M is also constant acceleration. Okay? Okay, there's a question here. In an electric field, does the charge particles follow the electric field lines?
It depends on the charge.
Okay, what does that mean? Louder.
Positive or negative?
No, that's not the issue. The issue, if I have an electric field line like this, does the charge follow it this way or no?
No,
It doesn't.
it doesn't.
No, forget what it is. It's just, why don't you guys listen? There's a good explanation to this in the book. You guys, who does not have the book? I guess some of you don't. I'm going to post the first 2 chapters PDF files on the blackboard for you to study from this weekend. Okay, but the answer, it depends if it is massless. If it is a massless charge, then it will follow the electric field lines. If there is a mass, then there are other forces that are going to affect it and they will not follow you. Okay, but there is a good, very nice paragraph on this you should read. There's only massless charge particles will follow the electric field lines. Okay, let's do a more sensitive example. Okay, we have 2 plates, okay, and each one of them is 6 centimeters in diameter, electrodes. One of them is positive, one of them is negative, and they're separated by a distance that's 5 millimeters. They are charged with by transferring that many electrons from one electrode to another. An electron is released. Remember they released? V0 is equal to 0, right? These released from rest at the center of the negative plate, here negative electrode. How long does it take the electron to cross from the positive plate to from the negative plate to the positive plate? What do you have to do quickly? Tell somebody. What do you have to do? First, find the electric field. Second, force. Third, and then find the one. Okay, let's do them. The first one, you need to find the electric field. Okay, the magnitude of the electric field, which is equal to what? Q over epsilon A. What is Q? He told you that we have that many electrons. Thank you very much. It's equal to this number, which is the number of electrons. 11 multiplied by the charge of the electron, which is 1.6 times 10 to the power minus 19. That's the charge of the electron if you don't know. Okay? Divided by epsilon, we know it from the previous question, 8.8 times 10 to the power of minus 12. And the area in this case is pi, right? And he told you diameter indicating what? It's circular, right? So diameter that we have to take the radius, which is 3 centimeters, which is equal to 0.03 squared. You get your electric field. Okay? So the electric field will be, do we have the answer? Somebody, do you have the notes? What's the answer? 6.4? Power 5 like this?
Yeah.
Okay. In Newton per coulomb. That's the electric field. Okay. So I got my electric field. And what's so special about this electric field?
It's uniform.
It's uniform. Thank you very much. And it has, what is the direction?
It's from
Positive to negative. Okay, so I know it. So if I know the direction of the electric field, and this is a negative charge, so the motion of the charge will be opposite to it. In fact, for this, it's easy. It's easier for you to see because this is an electron. An electron is negative, and this is negative, so it will repel towards the positive. Okay? So once I found the electric field, second one, you told me that we have to find the force, which is equal to Q multiplied by E. Q is the charged electron, which is equal to 1.6 times 10 to the power of minus 19, and the electric field is equal to 6.4 times 10 to the power of 5. What was the force? Somebody? Yeah. Somebody, you must have the answers. If you have the notes, the answers are there. Okay, so let's check here. That's E, and well, I did it in one shot. Okay, don't worry. We'll do it the same way. So if I found if here is equal to this, then from here I can find the acceleration, right? I can find the acceleration. A is the acceleration, which is equal to what? F over M, which is equal to Q E over the mass of electron. Yeah, so if you look here, just so that we get it, we don't have to. So this is done for you here. Okay, QE, that's E, right? The charged electron, right? Because the particle is an electron. Divided by the mass, and then you get the acceleration. A is equal to 1.12 times 10 to the power of 17 meters per second. Can somebody reflect on this answer here, this acceleration? Is it too big? Is it too small? Is it comparable? Too big comparing to what? Compared to gravity, the acceleration of gravity is what? 10, right? Let's say 10. Right? So compared to the acceleration due to gravity, G, let's call it G, is equal to 10 meters per second. How big this is? It's huge. The acceleration is huge in comparison to it. And that's why maybe sometimes you hear, when you're talking about electrostatics for charges of these small masses, we but we always ignore the effect of gravity. Because it's too small. Its effect is too small. Okay, so let me finish this and then we can come back to questions. Remember what the question is. He's asking you to find the time taken. Where is it?
The distance.
Yeah. No, an electron is how long? How long is the time? How long does it take the electron to cross from the positive plate, from the negative plate to the positive plate? So what does that mean? That means I need the time. Well, one way of finding this, since I know the separation, I can say delta x is equal to V0t plus a half a t squared. Well, this guy is 0, and this one is 5 millimeters, so 5 times 10 to the minus 3, right, to get it to meters. Get it 1, minus 1 to get it to centimeter, minus 2 to get it to meters. And then it's a half a t squared, so the only thing that you don't have is t. And then from there you can calculate the time. What do you expect the time to be? In what range? Very big? What do you mean by very small?
It moves fast.
See how small it is? It's 3 times 10 to the power of minus 10. So it's something like 30 nanoseconds. Yeah. This very short time. Why? Because the acceleration is very big. So the time taking the electron to go from the negative plate to the positive plate is very, very short. Reason why? Because the acceleration is so big. I'll take a few questions now. Somebody had a question. Yeah, start there.
Since like it's opposite to the electric field, the force, how come it's not negative?
Remember, the concept of negative is something to do with direction, right? Sometimes direction, sometimes increase, sometimes decrease. So the concept of negative in physics has a lot of meaning. Now in here, right, you say, okay, it's moving this way, right? The electron is moving this way, right? So it's really your definition of what positive is and what negative is. For us, all it matters is that going from here to there. If that's positive, fine. If you flip it, if this was negative and this was positive, we do the same thing except in the other direction. So the concept of positive and negative is not really does not really matter as much as the direction of the motion.
So like when we're writing Q, we don't use the negative.
In here,
Yeah,
But that's the definition of electric field. Remember, the direction, the magnitude of the electric field is equal to Q over epsilon. Now, its direction in this case is this way. That's it. If somebody asks you what the direction, you say, well, it's minus I time. But that's not what the question is asking. Yeah.
Certainly, why we use the charge of 1.6?
That's the charge of electron. Right? Because he told me he has that many electrons. 1 times 10 to the power of electrons. Now each electron has 1.6 times 10 to the minus 19. So I multiply that to get the total charge. Got it? Yeah?
Doctor, in the question, the resurrection electron is released from rest, and we said that V naught is equal to 0.
Yeah, released from rest.
Yeah, so since V naught is equal to 0, we have to use the kinematic?
No. The reason we use kinematics is because because the electrostatic field is uniform. Not because the initial velocity is equal to 0. Since the electrostatic field is uniform, then we use kinematics because the acceleration is uniform. Something else? Question? No more questions? Okay, so this is very, very good. I mean, we're doing very well in terms of time. Okay, everybody understands the concept of uniform electric field and how to describe the motion? Because that's our objective. Our objective is to describe the motion of a charge in a uniform electric field. Okay, all right? Let's do one more example very quickly, which is something that I already sort of alluded to. Now let's read the question together. The question says that we have an electron gun. Okay, there's an electron gun here, and creates it creates a beam of electrons that is moving with initially. That's not equal to 0, guys. Please, it's equal to v0 along the direction horizontal is equal to that much. So v0x is equal to what is it? 3.34 times 10 to the power of 7 meters per second. Okay. When it enters the electric field, the uniform electric field, this is an electron. What's going to happen to it? Yeah, it will be projected up, right? Just like the projectile motion which we described earlier. Okay, so the electrons enter at 20 centimeters. So this 2 centimeter long. He's talking about the gap. The gap is 2 centimeters, and also the length of the plate is 2 centimeters. Between the parallel plate capacitor and which has an electric field. He gave you the magnitude of the electric field. So E, the magnitude of the electric field, which is downwards, is equal to 5 times 10 to the power of 4 newtons per coulomb. In what direction and by what angle will the beam, the electron beam, is deflected? That means he wants you to calculate theta. Can somebody from physics 1 think of this as a projectile? And tell me what you want to calculate here. Yeah?
V0x, which is V0 plus
Maybe where is the direction we're gonna hit or
Let me ask you, this is a test of how much you know, how much you have left from physics 2. From physics 1. Not much, right? Okay, let me just say. Okay, now, this is projectile motion. You have a particle that is coming in, and then there's an electrostatic field, uniform electrostatic field, that's going to give you a force. There's still an electron, right? A force is equal to E multiplied by this electrostatic field. Huh? Right? Okay? And then this force will give you an acceleration. A is equal to Fe divided by m of the electron. So you get an acceleration. In this case, what is the direction of the acceleration? Up, which is opposite to the direction of the electric field. Why? Because this is an electron. This is a negative charge. We said negative charges move opposite to the field. Okay? So what do you have? You have a projectile motion, or a projectile that is going into an electric field, and it's being acted upon by the acceleration, this acceleration which is upwards. That's why it's going up. That means if I wanted to do this as a projectile motion problem, then I have to have two components, or two dimensions. So let's talk about the x and the y. So the x motion and y motion. For the x motion, Vx is equal to V0x. It's constant. Why is it constant, the Vx? Thank you very much, because the acceleration is along y. Right? This you should write that down. A is equal to AY, is along AY only, because the electric field is along y. So the V along the x-axis does not change. So when I wanted to calculate the angle here, let me take this out so that I use it. When I calculate the angle here, Vx, because the angle will be what? This is Vy, and this is Vx. My theta will be equal to tan inverse Vy divided by Vx. So Vx is there. Vx is still V0x, it does not change. Okay? My only problem is to find Vy. How do I find Vy? Kinematics again. Vy is equal to V0y
Minus GT.
plus or minus. Yeah. Plus AY T. Is that going to help me? Where's T? I don't have the time. Right? How about this one? Delta y is equal to V0y, right? T plus a half a t squared. Does that help me? No. Don't have the time. I can, well, if you want, because remember, V0y is equal to what? It's 0. Right, because it was kicked along the horizontal. So V0y is equal to 0. Let me just box this. Okay? So from here, since I'm given delta y, he told me it's equal to the separation between these two guys. He said it's equal to 2 centimeters, right? Right? 2 centimeters. So one way of doing this, since this is equal to 0, delta y is equal to a half a t squared. And I know a, so I can calculate t from here. And then I go back and I find Vy is equal to AYT. That's one way of doing it. Thank you very much. You can do the V0y, V2 squared, V2y, of course, squared, is equal to V0y squared plus 2a delta y. Right? You have a, you have delta y, you can calculate Vy. Okay? So this, if you want to do it in one shot. Once you calculate Vy, right, then you come in here and you say my theta is equal to Vy divided by Vx, and problem solved. Okay? Is that clear or not so clear? Yeah, we have one question here. You did not, that's what I expected somebody to ask this question. Can somebody tell us how did we calculate Vy? Vx is easy. Everybody knows how to calculate Vx? It's the same. Right? It's the same as V0x because the acceleration is along the vertical direction. Right? Right. So Vx will be the same. Right? How do we calculate Vy? First of all, yeah, we have the acceleration, which we calculated from here. This is my AY. Okay? And it's upwards, or the direction of the acceleration is upwards. And from here, and once I found that, then I say, okay, I know V0y is equal to 0. If you know this, and you know that, then the problem is solved. Right? Why is V0y equal to 0? Because it was kicked horizontally. If you forgot, V0y is equal to V0 sine the angle theta. What's the angle theta? 0. What's sine 0? 0. Sine 0 is equal to 0. So that means it's equal to 0. That's why Vy is equal to 0. Because he kicked it horizontally. Horizontally means theta is equal to 0. That's what he means. Second? If it's released, it will not go here at all. Right? If it is released and you release it outside, it's not going to go here at all. We just did that in the previous example. If you release it inside, then immediately it go up. Right? Okay. All right, so let me just very quickly go over take you through the solution. Because we have that's one of the advantages of having the PowerPoint posted. Okay, so the first thing that I've calculated AY, which again turned out to be very big. Okay, huge, guys, please. And then after that, I calculated delta t, which is simply the length, right, divided by Vx. I calculated the delta t, by the way, from x in this case. Which I don't have to do it, but I did it. And once I did that, then I calculated Vy, which is simply Ay delta t. It's the first equation, this one, because V0y is equal to 0. And once I calculated that, then theta is arctangent or tan inverse Vy over Vx, and it turned out to be 8 point, or something like 9 meters. Okay? Guys, this question is repeated now twice. If the initial velocity is 0 outside the parallel plane, it's not going to happen. Nothing is going to be affected. If it is inside, then if you release it, then it will go up. Right? So it will be this V0y is 0, and then it will go just like what we did in the previous exam. Alright? Any more questions? No? Okay, so there are more problems if you guys want us to look at them. Let me just, guys, before we go, let me just very quickly, because we ended the class last time with this and we'll repeat it again. Shh, guys, please, just two more minutes. So the electric field lines are lines that describe the strength of the electric field. So if they're dense, if there are a lot, that means the electric field is high. If there are few, then so the magnitude of the electric field is proportional to the density of these lines. Okay, so the number of these lines per unit area. That means there are some specific, very important points about the electric field lines. First of all, the electric field lines are always directed from the positive charge to the negative charge. So if you have two charges next to each other, it will originate at the test charge, the positive, and it will terminate at the negative test charge. The number of electric field lines is proportional to the magnitude of the charge and also proportional to the strength of the electric field. They are an indication of the strength of the electric field lines. For a parallel plate capacitor, away from the edges, the number of field lines per unit area is the same as, are the same, so they are parallel. I mentioned that a number of times. The lines are equally spaced, they never cross each other. So you don't find the electric field lines crossing each other. And one more point, which I forgot to mention here. The electric field lines, they originate at a positive charge and they terminate at a negative charge. Okay, so originate at the test charge, positive, and terminate at the negative test charge. So this, again, one more minute, very quickly. So if I have to, so this is called a dipole, an electric dipole. If I have these two charges, dipole 2, right? 2, that means two charges which have the same magnitude but opposite direction, opposite sign. So if I have, then this is what the electric field lines look like. Now, if I take, as you can see, if I take a square here and I count the number of field lines, that's this is an indication of the strength of the electric field. If I take the same square somewhere away, here I see that the strength of the electric field is less or small. If they are opposite sign, if they are the same sign, then what happens? This is what you get. So the electric field line is sort of because of the the repulsion effect. Okay? All right. So this is where we'll stop, and inshallah see you next class. Questions? I'll take questions because I know some of you have to leave. But can you?